Okay, so we're recording now. Let me get my whiteboard here. All right, let's see. All right, so I'm going to start on we're going to use the practice problems here. So practice problem set, I guess, number 10. And I'm going to start on problem number 17. So I'm going to spend a little time kind of drawing it out, and then we can make sense of it after that. I don't know what problem it is in the book. Anyway, so it says, so this is what's given. It says 95 cubic foot per second jet. Okay, and this is where the language starts to matter. A jet has a very specific meaning. It's moving in the positive x direction at 18 feet per second. At 18 feet per second. So this is unusual for them to give us both Q and V. Maybe we'll just write that as a V. The stream hits a stationary splitter such that half of the flow is diverted upward at 45, the other half is diverted downwards. So basically what's going on here is we've got this jet of water. Maybe I'll do the water in blue. And it hits this thing, this splitter. And the splitter is such that it's 45 degrees up and 45 degrees down. And so the water comes in and it hits it. And now the water is kind of, is being split. Half's going up, half's going down. And both streams have a final average speed of 18 feet per second. So we've got 18 feet per second coming in here. We've got 18 feet per second coming in here and 18 feet per second leaving. Okay, so that's, feet per second. Okay, disregarding gravitational effects. So there's no gravity here. So I guess G equals 0. Determine the X and Z components. So this is X and this is Z of the force required to hold the splitter in place against the water force. So required Fx, I'm going to go ahead and call this anchor equals what? And Fz anchor equals what? Okay, take the density of water is 62.4 pounds mass per cubic foot. Okay, we're never going to do that. So in the problem statement, it says rho equals 62.4 pounds mass per cubic foot. Okay, I hate that. We're never going to do that. We're going to take rho as 1.94 slugs per cubic foot. Okay, because a pound mass is a lamentable unit. Okay, that will screw up all of your problems and will screw up your life. So we're never going to use that. It would be like if we decided that from now on in the metric system, we were going to have a unit called the Newton mass, which is the mass that weighs 1 Newton on Earth. Like this, just really, it's ridiculous. Okay, so whenever you see that, just ignore it. It's dumb. Okay, so we're going to go ahead and solve this sucker, and so let's see, how should we do this? So the first thing we do on all these problems, and a lot of times we do this mentally, but it's a good idea to do it not mentally, is to draw like a control volume. And so the green is going to be my control volume. It's kind of like a free body diagram, but it's a little bit different in that a lot of times with your control volume, you will draw a free body diagram of the control volume. But I'm going to draw the control volume. And right now I'm drawing on the top of my picture, which is not necessarily correct, but that's what I'm doing. I'm actually going to delete this end because there really isn't an opening there. Okay, and the thing is, what we're going to do is we're going to analyze all the forces and all the fluxes. Okay, so what I typically do with my control volume is I draw my arrows. These are momentum fluxes. So this is, the water is crossing my control volume, my control boundary, or really what we call the control surface. Okay, at that point, once I've got all the momentum fluxes, now I'm going to do it like a free body diagram. I'm going to try to identify forces. And when we identify forces on these problems, there's always 2 types. There's a surface and body. Okay. And so the surface, well, the body forces, in this case, in this class is always gravity. Okay, if you go into another class, there might be magnetism, or I don't know, if you really get into some, real physics classes, maybe the strong force or the weak force or the nuclear force or something else. But in this case, it's just gravity. So surface forces, on the other hand, require thinking about really just forces in two particular spaces. So really this is like right here. Like, so we're going to think about all the surfaces of our control surface, or all the little miniature surfaces. And so what we've got on these edges is potentially we've got pressure. Okay, that's a force. We've got a little pressure right here, and we've got a little pressure right here. Okay, so pressure is one that we always want to look out for, and it's usually the least. It's not the hardest to work with. It's just sometimes we have to use Bernoulli to find it. In this case, based on the problem statement for this thing, so this is the vein that's on the outside of that thing. So based on the problem statement of this is a jet, which means that this entire thing is in the atmosphere. The only place it's not in the atmosphere is right here at the splitter. So basically the pressure all along here is atmospheric. All along here it's atmospheric. So we can say the pressure is atmospheric, which means we're not going to worry about it. We're going to make it zero gauge, which is awfully nice. Okay, so now we're still kind of identifying forces. So the last little kind of force that we want to deal with, so I should also note that there could be pressure up here, but it's zero everywhere basically because it's gauge. And so the last force that we want to deal with is basically this vein right here, which I've drawn in black. Normally wouldn't draw that on a proper free body diagram, but if I were to go in here and erase that vein and say, okay, well, it's gone. What effect did that vein have on our control volume? Well, it was certainly pushing on that water. Okay, and there's really two ways that it's pushing on the water. And so one is normal forces. So it's kind of pushing on the water like this. You can almost think of it as a normal pressure because it's almost certainly distributed over that vein. Okay. And then the other possibility is that there's friction between the vein and the water. So like all along that edge, okay, there's like a viscous thing. So basically it's working to slow the water down a little bit. And a lot of times, a lot of these problems will tell you to ignore that effect. I don't know what difference it makes to ignore it or not. Because what we do is we take all of this. So we take this normal force here and this frictional force, and we combine it into a single force. So I'm going to go ahead and draw an actual free body diagram of the water. Okay, that's my water. Here's my momentum flux, 18 meters per second, feet per second, excuse me. Come on, you can erase. Okay, feet per second, and 18 feet per second, and 18 feet per second. And all of this, so we got this normal force, and we've got this shear, and we've got it on top and bottom. We're just going to replace it by calling this an anchoring force right here, or not an anchoring force. Sorry, I'm going to call this, and actually I should write it on the surface because it's happening on the surface. So I'm going to call this force. I'm going to call this force. What do they call this? A splitter. Force splitter on water. So that accounts for all the reasons for the force, for what the splitter is doing to the water. So I'm going to call that the force Sau X. Okay, and then I guess there's also one in the Z direction. I think the Z direction in this case is trivial because it's going to end up being zero. And that should probably be kind of obvious here because there's no gravity. I'm not sure why they got rid of gravity on this problem. But it is what it is. Okay. So that's our free body diagram, and that's everything that we're going to account for. Okay. So we've got forces and we've got momentum fluxes. And the momentum fluxes happen where some amount of fluid having some momentum crosses our boundary or our control surface. So what we're going to do here is we'll do the momentum equation. And so there's lots of different ways to write it. And if you look through my notes, you'll see it a few different ways. I kind of like it like this. Oh, well, I put the arrow in the wrong spot. Some of the forces plus the sum in of rho VQ equals the sum out rho VQ. Okay, and before I get into this, I want to note two important things. Well, a few important things. One, the arrows. Note where the arrows are. Those are the vector quantities. Those are the things that have signs. So those are the things that we have to make sure that, you know, so for example, if I change this thing and I say, okay, well, sum of the forces in the x direction plus the sum in of rho VXQ equals the sum out of rho VXQ. Okay, so what I've just done is everywhere where there's an arrow, it gets an X. But the key here is that these things have signs, right? But the Q does not have a sign. Okay, this particular formulation, it assumes that this is steady. Okay, otherwise, I have to put another term in there. And we don't really want to have to deal with that. In this class, you never have an unsteady momentum equation. Really, that's a subject for kind of grad level fluids. It could probably be taught in this class. It just never really, it's just not, it just isn't for some reason. Okay, so, all right, so there's that. Okay, so the other thing to note is that, so you're like, well, what about signs on Q, et cetera, et cetera? Any other sign that might come into this normally would come in maybe in front of the Q, potentially. But the reason that that doesn't come in, okay, so you never put a sign in front of the Q, you're just always gonna leave it positive, is that we're deciding ahead of time whether it's in or out. Okay, if I put them all on the same side of the equal sign, you know, like we could make this sum rho VQ of all of the momentum fluxes, but then you'd have to think about whether or not it's a positive Q or a negative Q. And it's just, to me, it's a mess. So what we're going to do is you have to decide beforehand whether or not your momentum flux is in or out of the control volume. Okay, to determine whether or not it goes on the left-hand side of the equation or the right-hand side of the equation. Okay, so this is essentially a very fancy version of Newton's second law. Okay, so I'm just going to go ahead and do this on the aside real quick before we go. So Newton's second law, you know, we typically think of it as like this. Okay, in truth, I think it really, and I'm not exactly sure how he wrote it, but it's, you know, d by dt of mass times, so really it's kind of like this. And what this is it's saying that the sum of the forces equals the time rate of change of the momentum. Okay, and we typically basically say, oh, well, the mass is constant. We bring that outside, and then we're left with an acceleration. Okay, and there's nothing wrong with that. However, on a control volume, the thing is that inside this control volume, there's a few different reasons why the momentum could change. One is external forces, things pushing on that fluid like this and like this. And the other reason that, you know, is that we just end up with kind of different amounts of momentum leaving than what's coming in. Okay, so ultimately in the end, they all have to add up, you know, like why did this momentum change to this momentum? Well, it changed because this force existed. Okay, and so that's kind of what we need to drive at. So let's go ahead and start to work on this. So we always work downwards. So sum of forces in the x, we're going to split that out. In this case, we only have one force in the x. So that's FSOWX. Okay, and notice it has a sign on it. It's got a little x on it. So that force is negative. It's pushing in the negative direction. Okay, and again, like if we solve for it and we get a negative number, that means we assume the wrong direction. Seems like highly unlikely in this case because you know, the water's slowing down in the x direction. Like it's still going 18 feet per second, but it's no longer going 18 feet per second in the positive x direction. It's now going 18 feet per second at an angle, okay, which the angle is 45 degrees. Okay, so that's the only force because we have no pressure, we have no gravity, we really have nothing to worry about here. Okay, so now we're gonna go to the end. Okay, so the sum of the ends, well, we've only got one in, and that's right here. So we're gonna account for it. Rho of water. The V and the X, that's 18 feet per second. I'm gonna do this in what do you call it for a second? Symbols. So I'll call that V1. Okay, and then Q. Q is given over here. So I'm gonna call Q1. Q1. Okay, notice everything is positive here because Q is always gonna be positive. And then Vx is or V1 is in the positive X direction. Okay, now we've got two outs over here.
A question, Dr. Wagner.
Yes, sir.
Sir, do you have to multiply by the area of that section 1, or do you don't have to?
It depends. So if so good question. If right up here, if they didn't give us Q right here,
right,
then we'd have to calculate Q. So in that case, what I would do is I would go right in here and I would do V1 times area.
Okay.
Okay. But in this case, if they give us Q, just use the Q, right? There's no reason to do that.
All right.
Okay. Now the trick here, when that happens, is to make sure that you keep it as positive. Okay. No matter what the velocity is, you want this number, this Q, to be positive. Okay.
Okay.
This number has a sign. So this number is plus or minus, but this one has to have a positive sign. Okay.
Cool.
Okay. So I'm going to go back and I'm going to just keep it calling it Q1. Let's see here. So V1, Q1. And then for the outs, we've got two outs. So we're going to kind of split this thing into two. So I'm going to go rho water. So I'm just going to work downwards, rho water. And this Vx, okay? Remember, this thing has a sign on it. So I'm going to deal first with the one that's going upwards. Okay, so I don't know, maybe we'll call that V2. Call that V2. So say that's V2. It's got an angle, theta. V2, and this is going to be V2 cosine. I'll call that theta 2. Okay, and I'll call this theta 3. That way everything kind of lines up. Okay, so again, just remember that Vx has a sign on it. Okay, so it could be positive, it could be negative, but if there's a sign, if it's not, directly aligned with one of your axes, you're probably gonna need a sine or a cosine. Okay, and again, we need a Q right here. But so in the problem statement, hold on, I kind of lost that problem statement. Let's see here. Where's my problem statement? It says, I think it says that the water is split between the two. Where is it? Here we go. Stream hits a stationary splitter such that half the flow is diverted upwards and the other half is converted downwards, diverted downwards. So this right here is going to be Q1 over 2. And this down here will be Q1 over 2. So basically that Q is being split in half. So again, remember there's no sign on the Q's. So it looks like that. Okay, so that's for location 2. And then we're going to do the same for location 3 down here. And I don't think there's ultimately going to be any difference down here. But let's see here. The density of water is the same. We're going to have V3. Okay, V3 cosine of that same angle. I'm going to call it theta 3, although in this particular problem, it's 45 degrees. But you could imagine that, as a typical twist that, these problem makers like, or that, me, your test maker, likes, is to just change the angle, maybe make this angle 30 or, 60 or something. And then this becomes Q2 or Q1, excuse me, over 2. Okay. So at that point, now we're just going to start plugging stuff in. Okay. And I think we have everything except F SOW X. Okay. F SOW X. So F SOW X plus, let's see here, rho X, rho W 1.94 slugs per cubic foot. If you use pounds mass per cubic foot, you're going to have to divide by 32.2. So don't use pounds mass. Just, this way will always work out for you. V1 is 18 feet per second. Okay, Q1 is 95 CFS. Okay, equals, And these two terms end up, they're exactly the same. So I'm just going to go ahead and I'm just going to kind of combine them into one term with just a Q1. So basically it's 2 times the first term, which means this 2 on the bottom is going to go away. So I'm going to be left with 1.94 slugs per cubic foot. Okay, V2, which is 18 feet per second. Okay, cosine of 45, times, we're just going to say Q1. So that's going to be 95 CFS. Okay, if no one sees what algebra I did right there, please let me know.
I got a question again.
Sure.
Why is the cosine instead of sine? Like sine of 45?
Well, cosine and sine are the exact same thing, but in this case, we've got the V is going like this, and this is my angle. So let's just say it's a theta. I mean, 45 is obviously special. And so we want the portion of that's going in the X direction.
Okay.
Okay, yeah. So it's that's the adjacent side. Okay. So what we're gonna do now is we just plug and chug this into the calculator. And just a real quick note on units, because a lot of people don't necessarily love slugs. But okay, feet cubed right here cancels with cubic feet right here. So now I'm left with slugs foot over second squared. So if you think back to like basic, chemistry, F equals ma. M is a slug, acceleration is a foot, acceleration is foot per second squared. So this is a pound. Okay, so that's how we know that we've done this correctly. If you plug in a pound mass right here, this will not work. Okay, so it has to be a slug. Okay, it's just like with you can't plug in grams where you mean mass for in the SI system, or it won't work. Okay, so anyway, so let's go ahead and solve this real quick. We've got a lot of similar terms here. Anyway, 1.94 times 18 times cosine 45 times 95 equals, I'm just gonna subtract it all out. Minus 1.94 times 18 times 95. Okay, so we end up getting that, and if we keep track of our signs here, F SAO X equals 971.64 pounds. Okay, and it has a positive sign on it, which means we assume the correct direction. So I'm going to go ahead and write this over here. F SAO X equals 971.64 pounds. Okay, because we're going to do the vertical one here too, even though it's trivial, just because this is kind of your first time seeing this. So I want to make sure that that we get as much practice as possible. Maybe I should have started with the vertical. Let's see here. Okay, so I'm going to erase all of this. Okay, let's see. Maybe at this point, some of you probably haven't even watched the video yet of me, presenting this this equation. So there's also the possibility that's not obvious to you that it's trivial, which would be totally normal. For me, I've looked at these for 20 years now, so you get a certain intuition from doing that long enough. All right, so now we're going to go in the y direction, the z direction. Sum of the forces in the z plus the sum in of rho vz q equals the sum out rho vz q. Okay, you guys should also note that I do my v's without a little cross on it. So if I put this, that's a volume. This is a v, a velocity. So just kind of be aware of that. Not terribly important, but we haven't really talked about velocity very much. And now we're there. So all right, so the forces in the z, the only force in the z I have is this F SAO z. So F SAO z. Now notice it's got a sign, it's going upwards. So I usually like to put a little extra positive sign on there. Obviously, you don't have to, but what that positive sign does is it reminds me that I've checked the sign on it. Okay, so now we've got an in plus. So this is an interesting thing, because let me go ahead and erase these circles so that I can do them one at a time. So we're going to go here and let's look at this one right here. Okay, and this term goes away. And the reason it goes away is because this right here, it has a direction, and this direction is z. And the z component of a force going to the right is 0. Okay, q still exists because q is always positive. Rho is always positive. Those are scalar values, so those don't matter. But this vz goes to 0. So that whole term goes away. Okay. So now we're going to go in the, so now we're going to look at these other two terms, and hopefully now you're starting to see why this thing is going to go to 0. So we've got this thing right here. Okay, and we've got the sum of out. So we've got two different terms. So I've got rho, 1.94, okay, rho of water. Okay, Vz, which is going to be V2, this time the sine of that 45-degree angle. Okay, and then Q, or I guess Q1 over 2. Let's write it as Q1 over 2, okay, because that's our Q flowing through that opening. Okay, and then we have to add the other one, okay, because we're summing these, so we've got two of them. So here's the other out down here. Okay, and so we've got rho W. Okay, again, it's V, this time it's, I guess it's V3 sine of theta 3, but there's a negative sign on it because it's going downwards in the z direction. Okay, so I'm going to plug in, and this is still going to be Q1 over 2. Okay, so here you can see, you know, theta 1 and theta 2 are the same. V3 and V2 are the same. Rho W is the same. Q1 over 2, Q1 over 2. These are exactly the same. They just have a different sign, so they add up to 0. So if you do, you know, if you want to plug all the numbers in and solve it, you can, but this just equals 0. Okay. So now we've got, you know, our two forces. So F sau Z equals 0. Okay, any questions on that before I erase it? Apologize, it sounds like the working trucks are coming today. Okay, so I'm going to erase that one. Let's see here. All right, so the last bit though is, like, it seems like we're done. And I made a pretty fundamental error when I was doing this. But it's an important error, and it's one that's important to talk about. Okay. And so we've got these two things, but what it asks for is it asks for the force to anchor. And what it wants to anchor is you want to hold the splitter in place. So if I draw a free body diagram of the splitter, here's what it looks like. Okay, so the splitter just looks like this. Okay, and it's got forces on it. Notably, okay, can you move on, buddy? That's really annoying. So what we can do if we draw the free body diagram of the splitter, okay, it's basically, so I'm going to take this force right here, F SOWX, which I suppose actually I should do like this. Let's do it like this. Equals negative, right? So I'm going to kind of make it a vector like that. This, of course, is trivial to make it into a vector. But anyway, so the force, so this force right here, I'm going to call force water on splitter in the x direction. So I split the order of my my letters to indicate that, you know, these two forces are equal and opposite. Right? So this one was in the negative direction. So this one's in the positive direction. Okay, F SOWZ is kind of irrelevant. Okay, so we're not even gonna bother drawing that one. All right, so why doesn't the splitter just fly away? Because it's got a force on it in the x direction of 971 pounds. Why doesn't it fly away? Well, the reason it doesn't fly away is because there's an anchoring force. There's something holding this thing in place. Now, we don't know what it is based on our drawing. You know, maybe somebody's holding the splitter, maybe it's attached to a wall, who knows what it is, but there's another force right here that is anchoring it into place. F, what do I call it? Fs comma anchor. F, X comma anchor. Okay. And that's the free body diagram of the splitter. So this becomes a fairly trivial problem. I say, okay, well, the sum of the forces in the X equals 0. So the F anchor equals F water on splitter X. So I could say that, F X anchor equals F WOSX, which I happen to know is 971.64. So I can say that FX anchor equals 972 pounds. All right. Now, I want to talk a little bit about my error here. It wasn't really an error because we still got the right answer. So what we want to do here, and this is kind of important, is that when choosing your free body diagram, so it depends on what the question is asking. So if the question is asking, and this happens pretty regular, and my mistake was not looking at what they asked for. They asked for the anchoring force. So if they asked for the anchoring force, what you want in your drawing is you want the anchoring force to be included. Okay. What I did is I ignored that. So I forgot about that. And I treated this as if what they wanted to know was the force of the water on, the water on the splitter or the splitter on the water. So if you want the water on the splitter or the splitter on the water, if you want F SOW or F water on splitter, okay, then you want to do a free body diagram of the water, which is what I just did. Okay, I drew the free body diagram of the water. That's what this is. The problem with that is that still leaves you one step away from your solution right here. Okay, so you have to do plus a step. So that was a mistake on my part. Okay, and actually, this is a common mistake on my part. I do it all the time. If you go through my solutions, you'll see I make this mistake all the time. A better guess, though, when you have this, is you want to do a free body diagram of the water and, in this case, the splitter. It could be the water in the nozzle, the water in the, whatever the other thing is. Because if you draw that free body diagram, and I'll go ahead and draw that for you right now, okay, because it's not like it's harder to do that. In fact, it's not harder at all. So let me, erase real quick, and I'll show you how this would have been easier. And it wouldn't have been any different, especially not for this one, which didn't have any gravity. So instead, what we would draw is we would draw a free body diagram, and it would look like this. And here's my water coming in. Like that. And I would have drawn my fluxes. So here's a flux here, 18 feet per second. Here's a flux here, 18 feet per second. Here's a flux here, 18 feet per second. We decided that all the pressures were 0 because it opened to the atmosphere. And then we've just got an anchoring force right here, F anchor. Okay, and this one's in the X, or well, FX comma anchor. And it turns out there's nothing in the Y direction, but that would have been an easier way to solve this. Okay, so if it wants, the anchoring force, make sure that the anchoring force is on the edge, is on your free body diagram, because that'll just save you some time. Okay, and so this was a mistake that I made this time, and I'll try not to do it on the next one. Any question? Okay, so we're going to move to a harder problem. We've got about half the time left. So I think we should be able to solve this one, and that'll probably call it a day. So I'm going to go to number 21. 21, let's see, let's clear all drawings here. Okay, so 21. Okay, water flowing steadily. So I like this one. You should know already that what's going to happen when I pick problems for the test is I'm going to make sure that you have to deal with signs. Okay, I need to know that you understand how to deal with the signs. Okay, so this is given is a little diagram. And you'll note that there's a sign problem here, right? There are some signs that are going to have to be dealt with. Okay, already, like the water on this end down here is at an angle. Okay, and they kind of draw it like this. So you know this angle is 60 degrees. Okay, the water's entering right here. This pipe has a diameter of something. I don't want it right there. Okay, there's a diameter right here, which I believe is given, 30 centimeters. Just go ahead and label it as 30 centimeters, 0.3 meters. Okay, I always like to convert as soon as possible. This diameter down here is 10 centimeters, 0.10 meters. Let's make that a 0. Okay, there's some height between these two, which is 50 centimeters. Let's see here. Water flowing steadily at a rate of, they say, Q equals 0.23 CMS. Again, that's cubic meters per second. Okay, one of my most common errors is when I give CMS on a test, people think that means centimeters per second. But note, this is a flow rate, so it can't be centimeters per second. It has to be volume per time. So it's deflected downward by an angled elbow and exits. So that much flow rate is deflected downward by an angled elbow and exits to the atmosphere to atmospheric pressure as shown in the given figure. Okay, so if the water is exiting to the, oh no, that's an eraser. If it is exiting to the atmosphere, then usually it will be drawn like this. The key thing to know there is that means that there's no pressure right there. Okay, so that's the key to it going out into the atmosphere. So a lot of times I'll call it a jet. If they say the word jet, that means it's going out into the atmosphere. If this little thing is drawn right here, that means it is in a pipe and it has pressure. Okay, so just be aware of that. Doesn't mean they're telling you what the pressure is. It just means that it exists. Okay, so determine the force acting on the flanges of the elbow. I haven't drawn the flanges yet. And the angle its line of action makes with the horizontal. Okay, so basically there's something right here. It's like a clamp. And they put some bolts in here. And this thing is keeping this elbow from flying away. Okay. Now, hopefully, I'm hopeful that you guys can imagine this. Like if you were holding this elbow, like if you're standing here and you wrap your hand around this, let's imagine these are your fingers and you're holding it. Hopefully you can imagine that this thing is it's gonna be pushing on your hand, right? So that's why this thing has to be bolted to the wall. Okay, and hopefully you can imagine which way this thing is gonna be kind of pushing, right? So at least partially, I like to think about the problems before I work them, so I kind of get an idea what's going to happen here. But hopefully you're imagining okay, well, this water is coming in and it's hitting this wall, it's hitting this bend and it's turning back. So I'm going to have to be pushing. It seems like I'm going to have to be pushing in this direction. Okay, if I were holding it. So in other words, it seems like this flange is going to have to be pushing in that direction. It also seems like, almost like this is kind of almost like a little rocket ship or something. So it's going to kind of be making this thing want to move upwards. I'm going to prevent it from moving upwards by pushing downwards. Okay, so this is my hypothesis for this question. Okay, that it's going to look like that. Okay, now I've been wrong before. I don't think I'm going to be wrong in this case, but anyway, so we have a few other things to note. The internal volume of this thing is 0.03 cubic meters. So that's the volume of the water inside the bend. And it says that the elbow itself, so the mass of disregard the weight of the elbow. So the weight of the elbow equals, you know what? I'm going to put a weight of the elbow in here just because I want that to exist. Okay, so let's go ahead and just, okay, it means we're going to have a different answer than the book, but I want to show you how to deal with the weight if the elbow had a weight. Or what will happen a lot of times is they'll give you the mass of the elbow. If they give you the mass of the elbow, okay, I've got a mass. You're just going to multiply times gravity. So that's the metal material that makes up this, or it could be rubber, I guess, or whatever they make this elbow out of, plastic, PVC. So it's whatever the elbow itself is made out of. Okay, and then they say disregard friction effects, which is not necessary. We're not going to disregard friction effects. Take the density of the water to be 1,000 kilograms per cubic meter. All right, so, okay. Actually, there is a reason to disregard friction effects. Okay, so no friction, and I'll talk about that in a second. Okay, so required, they want to know, determine the force acting on the flanges. Okay, F, let's call it anchor. Okay, and I'm going to put a little arrow at the top because that means we want magnitude and direction, because they say line of action with respect to the horizontal. Okay, so that's a lot of talking to set it up. Okay, so now here the key is the free body diagram. So I'm going to do it up here because everything depends on that. Okay, and so in this case, we want the force on the anchor. So we're going to draw a free body diagram that looks like, so here's my control volume slash what I'm going to draw the free body diagram of. And it's going to include the flange itself. It's not going to include whatever the flange is attached to or whatever's holding it in place. Okay, so here's my free body diagram of my control volume. Okay, my control volume includes the metal or the rubber, whatever the flange is made out of and whatever the elbow is made out of. Okay, so we're going to draw that as best I can. You know, whatever that looks like. Okay, and I'm gonna, you know, it's, if I had more time, I could be a little bit more exacting with this. Let's see, we forgot the flange. Okay, and then this is like this. Okay, so when drawing a free body diagram, in this case, we want to think about forces, we want to think about surface forces, body forces, and momentum fluxes. Okay, and I'm gonna do the momentum fluxes, I'll do those in blue. We've got a momentum flux here. We've got a momentum flux here. Okay. Now we want to think about the forces. Okay. And so we want forces on the outside of this thing. So I'm not really worried about the forces on the water itself, except along this face and along this face. Okay, because everything else is internal to my system. Those two are actually on the edges, right? Everywhere else along this wall, this is all like the outside of my system is just, you know, metal, right? And nothing's touching that metal, at least not as far as we know. So there's no forces there. Okay, so this one right here, this spot right here, this has got, so we're doing the surface forces. This has pressure. This has pressure. The pressure here is atmospheric. Okay, so that one goes away because it's a jet. The pressure here is not atmospheric. So I'm going to draw it like this, like that. Okay, I'm going to go ahead and call this point right here. I'm going to call it point 1 because I want to be able to label it. I'm going to go ahead and call this point 2. Okay, so this is going to be V2. This will be V1. This force right here is going to be P1 times that area. Okay, and there's no pressure down here, so we're not going to worry about it. Okay, what other forces might we have? Okay, well, let's see. Here's our coordinate system. We're going to go X and Z. And so, well, let's see. So because I included the weight in my control volume, I've got the weight of the elbow. Now, I don't really know where to put the weight of the elbow, but let's go ahead and put it right there because whatever. You know, as long as it's on my diagram, I'm happy. They gave me the volume of the water. That's because there is a weight of the water. So the weight of the water. Okay, those are my body forces. Let's see, what other forces do we have? Okay, surface forces. So generally in this problem, we deal with pressures usually. And then there can be things pushing on the water, but in this case, there isn't, because the only place that, you know, because, you know, all of this area right here is all internal to my drawing. And then on the outside, there is no water. There's nothing touching all of that. So the last forces that we need here. So let's see, surface, body is the weight. And then the last thing we want to do here is there's this force right here to hold this thing in place. And so we've got these two forces. okay? And I put them at the flange, but you could put them anywhere. In fact, most of my work, I draw them here. Let's just draw them there, just because it's a little bit less crowded than up here, okay? It actually is acting at the flanges. But we'll call this F anchor X and Y, okay? X and Z, sorry. F anchor Z. And I know that my guess is that both of these are going to be negative, but I'm not going to worry about that. I like to draw them positive and solve for them. And that way, if I get a negative sign, it just means I got a negative force, or the force is in the negative direction. Okay. All right. So that's kind of a lot. Okay. So let's go ahead and let's look at our momentum equation. I'm going to do it in the X direction first. Sum of the forces in the X direction. Oh, not an equal sign. Plus rho VXQ. Okay. Summation. Excuse me. Come on, you can erase. Summation. Okay. These are the ins equals sum of the outs of rho VXQ. Okay. Remember Q, okay, doesn't have a sign. Rho does not have a sign. Okay. VX does have a sign. And of course, this is why I love this sort of problem, is because it's got signs in it. Okay, now what's the problem here? Well, we're going to have some problems. Okay, we haven't gotten to them yet, but we are going to have some problems. So first, I want to identify my forces in the X direction. So the first one is P1A1. Okay, so I'm going to say P1A1. That's in the X direction. That's positive. Okay, note that that force has a sign to it. Okay, so it could have an angle to it too. So it could be P1A1 sine of an angle if the entrance was at an angle. Okay, but in this case, that's not the case. Okay, so what other forces do we have? Well, we've got F anchor X plus F anchor X. Okay, cool. Any other X direction forces? It doesn't look like it. So let's go ahead and move on to all right. So the Z direction is, the up down direction is always more complicated, but not a lot more complicated. Usually it just means you have to include in weights. All right. Now, otherwise, either direction could be harder if just depending on which ways the openings are. Okay, so now we're going to do plus. Okay, the sum ins. Okay, well, we've got one in, and we've got this V1 right here. So we're going to deal with that one right there. Okay, so it's going to be rho 1, which in this case is just rho. There's only one rho in this problem. V1, which note, okay, I'm going to put a positive sign on it to remind me that I've accounted for the direction. And then Q. Okay, equals. Okay, we only had one, inlet, and we only have one outlet. So that's V2. Okay, the sum of the outs. So we've got rho. Now this is going to be V2. It looks like it's going to have a negative sign because it's going in the negative X direction. Negative V2. And there's an angle here somewhere. That's like 60 degrees right here. Okay, so this is going to be V2 cosine of 60. I usually prefer to have a theta till the end. Let's just leave that as theta. Okay, and then Q. Okay, note that Q1, the Q's are the same because everything that comes in here has to leave here. Okay, so there's no other place for anything to go. All right, so hopefully, if you followed that and you're thinking kind of one step ahead, you're probably seeing some problems here. Okay, well, we can get this area pretty easy, but what's that pressure at 1? Okay, what about these velocities? Okay, and so if you remember me when I work Bernoulli, I often like to think of terms of a master equation, and then kind of like an aside. So over here we're going to do some asides, and what the asides are going to do is they're going to help us solve for the things that we need. So we don't have V1 or V2, so we're going to use continuity for that. And I'm going to say that Q1 equals Q2 equals just Q, because we only have one Q. Okay, so what I would say is for Q1, I'll say V1A1 equals Q. So V1 is not given, so we have to solve for that. So let's see. So it's V1 is V1 times area 1, which is pi D1 squared over 4, okay, equals Q. I'm sorry, let's get rid of that D1. All right, let's just go ahead and plug in our 0.3. Come on, give me that. Okay, 0.3 meters squared. Okay. I also need this area, don't I? So I'm going to go ahead and add in a step so I can get this area for right here. So pi times 0.09. Let's see here. Pi times 0.09 divided by 4 equals some ugly number. So for my area, I'm going to say 0.070686. Okay, 5 sig figs. That's meters squared. Okay. Oh, and over here, my Q is 0.23. 0.23 meters cubed per second. So we're going to put that area underneath it. And we're going to get, we're going to get V1 equals 3.2538 meters per second. Okay, and V2, you could follow and do that exact same calculation, or you can note that, look, this one is 3 times as big as the one down here. So by continuity, then the velocity down here needs to be 9 times as big. Okay, so V2 is going to equal that same number times 9. So multiply times 9, and we'll get 29.285. So that's going to be a shortcut if you can see that. Okay, or you can do this calculation again at V2. Okay, so now we're good. We've got V2. We know the angle. We know Q. We know Q. We know V1. We know rho. Okay, this is what we're looking for. We know A1. And so now all we need to do is get that pressure. Okay, now my guess is, like, if you were like me when I took this class, you don't necessarily know how to get that pressure yet. But I'm going to steal a little bit of space so that I can do it. Okay, and what we're going to do is we're going to do to get pressures. Very commonly, well, usually you use a manometer if you can, but on these problems, it's most common to use Bernoulli to do that. For some reason, I have green here. Let's not do green. Okay, so what I'm going to do is I'm going to go between the 0.1 and the 0.2, and I'm going to do Bernoulli, P1 over gamma, because notice it's got our P in it. Z1 plus V1 squared on 2G equals P2 on gamma plus Z2 plus V2 squared on 2G. Okay, so one of the things here that I was kind of arguing about with myself about is whether or not you need this no friction. The no friction is what allows you to use the Bernoulli. If there is friction, then you have to assume there's no friction in order to use Bernoulli. You just have to go, well, I'm going to pretend that there's actually no friction because I want to be able to solve this with Bernoulli. Usually on a bend that's this small, it's only 0.5 meter. You might say that I'm going to use Bernoulli because maybe there's some energy loss due to friction, but it's not really going to be a huge number. Okay, so hold on. I'm going to turn on the fan. I'm going to close this door. The neighbor's dog is barking. Let's see here. Like my Rocky, who is a perfect angel all the time. If you don't know, Rocky is the perfect dog. Just letting you know that. So one of the nice things about this problem too is it allows us to do a little bit of Bernoulli practice. So what we're going to do here is, so I'm just going to solve going back from 1 to 2. Now it's fortunate in this case, I didn't actually plan this, that I did continuity first because we're going to need those numbers over here. Okay, so don't get too discouraged if you start doing Bernoulli and you're like, well, wait, I don't know V1 and V2. Usually a lot of times there's another way to get them. Okay, so let's go ahead and let's start plugging in. We want P1. So we're going to say P1 over gamma. Gamma in this case is the gamma of water. So, okay, so I'm going to give you 3 seconds. You should know what the gamma of water is. Some of you right now are fumbling through numbers in your head. Make sure that if you don't know what it is, like really fast, write down on a sheet of paper what the gamma of water is in both unit systems and what the rho of water is in both unit systems. Okay, and some of you are going, it's like 64 point, well, it's actually 62.4 PCF. Oh, wait, no, it's not 62.4, right? You have to remember. Thank you. You're exactly right. Well, brilliant, good, nailed me. Here I am talking trash, and you came and made me eat it. Okay, perfect. All right. So now we have to deal with Z1 and Z2. Okay, so for that we need a datum, and I usually like to make my datum my low point. So like down here or down here. Okay, so Z1 is going to go away because it's the datum. Okay, Z2 then is going to get that 0.5 meters. Okay, 0.50 meters. Okay, so we'll go plus, and now we got V1 squared, so 3.2538 meters per second squared over 2, and my gravity is 9.81 meters per second squared equals P2 over gamma. Okay, so now we're going to go to P2, look right here, and we'll note that P2 is in fact 0 because it's atmospheric. So we're going to get rid of that by saying, oh, that's atmospheric. Okay, now we've got our 0.50 meters from Z2. And then here's our V2, plus 29.285 meters per second. Okay, and we're going to square that over 2 times 9.81 meters per second squared. Okay, normally I like to look at all these terms to compare their order of magnitude and things like that. But what I want you to note here is that this is the dominant term right here, far and away. Okay, it's not even close. Actually, let's go ahead and do that. But you should see that 30 squared here compared to 3 squared here. 30 squared is what, 900, and then 3 squared is like 9. So this is the dominant term. So basically, all this pressure right here is going to be, is essentially being converted into velocity leaving this thing. Okay, so let's go ahead and solve this. Let's see here, 3.2528 squared divided by 19.62. So this term, I don't know that I have the space here. I'm going to work up real quick. 0.53928. That's meters, equals 0.50 meters plus 29.285 squared divided by 19.62 equals 43.711 meters. Okay, P1 over gamma plus. Okay, and this is gamma of the water. Okay, so you can see this is the dominant term. Okay, these two almost cancel each other out. So basically the velocity head that comes in. Wait, oh, I made a mistake. Huh, you guys did not catch me. What was my mistake? Did y'all see it? It has to do with my datum.
Should the 0.50 be negative?
Yeah, so the 0.50 could be negative. That would be one way to solve my error. However, in this case, I made this my datum. So I made this my datum. So Z2 should be the datum, and Z1 should be the 0.50. Okay, that's another way to do it. I don't like to deal with negative distances if I can handle it. So yeah, so that's an error. Okay, unforced. Okay.
Is that because like the flow stuff on the top, and then like you called that a 0.2, the one you did a data on?
Yeah, you could call either 1.2 or either 1.1. I like to go from 1 to 2 because with Bernoulli it doesn't matter. But when we get to energy equation, it does matter which one's 1 and 2. It has to go from 1 to 2. So it's just a good habit to get into. But in this case, I made this one 2, like early on in the problem, and I made this one 1 early in the problem. So if this is the datum, then all that really matters is that 0.1 is 50 centimeters higher than 0.2. So I could make 0.1 my datum, and then 0.2 could have a negative 50. Or I could make 0.2 my datum, and then 0.1 could be positive 50, which I think is probably a better way to do it. So anyway, so Yeah, did that answer y'all's questions? Sorry, it was a, it was a, boneheaded mistake. Okay, so we'll go ahead and solve this, and I'll just say P1 equals, it looks like it's going to be about the pressure head's about 42 meters, which is pretty impressive. Minus 0.5, minus 0.53928. Okay, times 9810, and we get a big number. Your pressures oftentimes are pretty big. 418, 610. Okay, and this is newtons per meter squared. So note that, one of the reasons that pressures get big is that we typically use kilonewtons, like it comes out more often that way. But this is okay for now. Okay, we like this for plugging into our bigger equation. Okay, so this is a nice problem. It's got a lot of everything going on. So now we're going to go ahead and we're just going to start plugging it and chugging. Okay, and what I'm going to do is I'm going to leave this pressure here so that I can plug it in. Okay. I mean, the actual numbers don't really matter. Hopefully at this point, most of you are going, yeah, I know how to do this at this point. Okay, so here, these are all of our asides. I just like to erase my asides. But I'm not in a traditional classroom where there's so much wonderful, whiteboard space. I'm still learning how to use this very limited medium here. Come on. We don't have all day for this. People got things to do. Come on. This is unbelievable. All right, forget it. All right, so 418. So this is something to be careful of. A lot of times they'll give you your pressure in the pipe because they'll be like, we don't want our students to spend the time doing the Bernoulli. We've tested the Bernoulli already. We want them to spend time, showing us they know how to do the momentum equation. That's fine, but they'll give it to you in kilopascals. So just remember when you do that, that probably all these other terms are going to come out in just newtons. So you want to make sure that you get back to just regular pascals. Okay, so we need that area 0.070686 meters squared. Okay, plus F anchor in the X. Okay, plus rho. The rho of water is 1,000 kilograms per cubic meter. V1 squared, whereas V1 is down here, 3.2538 meters per second. Okay, Q is 0.23 meters per second, or CMS, equals rho 1,000 kilograms per meters cubed times negative V2, 29.285 meters per second. Oh, I forgot my cosine in there. Come on. Times cosine of that angle, which is 60 degrees. Okay, and then Q, which is 0.23 meters CMS. Okay. Now you'll notice that the momentum flux terms here and here often have a lot of things that like a lot of similar numbers. Like the rows and the Qs are usually the same, especially if it's like one inlet, one outlet, the rho and the Q will be the same. So a lot of times people will kind of combine these on the same side so you can pull them out algebraically. That's fine, but I don't care about that right now. Okay, I'm just letting you know that you can do that. So you'll see, for some of you will click around YouTube looking for other ways to solve these. And so a lot of people will combine those on the one side. I like to keep them separate because to me, it makes the signs easier. And the signs are the biggest problem that my students face. Okay, or at least, yeah, generally speaking, that's the case. And for me, it's also the most confusing thing. But if you find another way that works for you, by all means, feel free to use it. Okay, so now we're in a calculator thing. So 418, 610 times 0.070686 equals. So this is 29,590. This is newtons plus F anchor X plus 1,000 times 3.2538. Most common error is people putting gamma right there times 0.23. So 748, excuse me. 748.37. Okay, again, notice the units. This is another way that you'll know if you're screwing it up. So those cancel. And we're left with kilograms, meters per second squared. Okay, so that's a Newton. Okay, equals, and this is going to have a negative sign on it. So let's see here, 1,000 times 29.285 cosine 60 times 0.23, and that equals 3,367.8 newtons. Okay. So we're going to go ahead and solve for all that. And we're going to end up with F anchor in the X direction equals, so 48.37, 9,590 equals 3,307.06 newtons, or F anchor in the X direction equals 33.7 kilonewtons. Oh, wait, sorry, negative. Okay. So we drew it the wrong direction. Okay. Now, a lot of times on a test, what I'll do is like, I'll set up a problem like this and I'll tell you to either work it in the Y or the X direction, because if you can work in the Y direction, you can work in the X direction and vice versa. And it's just me testing to see if you can do, one direction instead of both. Okay. And so that's this sort of problem in a nutshell. We've got 5 minutes, so I'm going to go ahead and set up the Y direction. We might even be able to solve it because we don't have to do Bernoulli and we don't have to get those velocities. One of you will have to speak up because I don't have those anymore. Well, I guess I have them right here. Here we go, 3.2538 and 29.285. Okay, so I'll still have those, so we can use them again. Okay, so let's go ahead and do this. And I'm going to assume that this wanted the magnitude and direction. So we may not have enough time, but I'm going to assume that if you have X and you have Y, that you guys can get the magnitude by doing Pythagorean theorem, and you can get the direction by doing the inverse tangent of the opposite over the adjacent. Okay, so that's how we would solve that. Okay, so I'm going to erase all this all the way up to my momentum equation, because we're going to do it in the Y direction. The only difference in the Y direction is that we've got weights. And we have to include the weight of the bend, because I included the bend in my, or the elbow, because I included that in my free body diagram. Okay. But some things are easier. Like I don't have to deal with the pressure in the Y direction or the Z direction, because it's not acting vertically, right? The pressure is acting in the positive X direction. Come on, man. We don't have all day for me to be. This is just ridiculous. All right, come on. You can do it. It's really not that complicated. It's just an eraser function. Thank you, Zoom. You're the best. That should be like the statement of the pandemic. Thank you, blank. You're the best. All right. So what I'm going to do now is I'm going to erase all these X's if it will let me. And we're just going to make them Y's. Okay. And what's cool about this thing, VY. What's cool about this is that we can get to a point where, okay, so let's get rid of this because that's kind of confusing. Okay, so the force is in a Y. We're just going to look back at this thing. I'm going to, somebody needs to mute themselves. Let me see. Okay, it looks like we're all muted again. Okay, thank you, whoever that was. Maybe that was iPhone 2 who was floating around being anonymous. No. Okay. All right, so the forces, let's see, in the Y direction, or the Z direction, excuse me. Oh, dadgummit, these are Z's. Z, Z, Z. Okay, so let's go ahead and circle them. I'll do them in blue. Let's see, we've got this anchor here, we've got this weight here, we've got this weight. Okay, there's no pressure in the Y direction. So that's pretty straightforward, right? So F anchor in the Z direction, that's positive, minus the weight of the water, which we can get pretty easy from here. minus the weight of the elbow, wellbow, if you will. Okay, done. Okay, those are all the forces. Now we need to look for momentum fluxes in the x direction. Okay, notice as far as in the z direction, as far as in, this is in the x direction purely. It has no z component, so we're not worried about that one. So we're going to get rid of that term. Equals. So now we've got outs, and we've got this one right here, down here. This whole thing down here. Right, so I'm gonna, and it's only one of them, so it's going to be the row of water times V2. Now this is a V in the Z direction, so we need it to be, so it's going downwards in the Z direction, so it's a negative V2, and it's going to be the sine of that 60 degrees. Okay, and then here's our Q. Okay, so I ended up being correct in the X direction. Okay, the Y direction is always a little bit more complicated because there are reasons that the force on it. So I said, based on this jet down here, that this force we should be pushing downwards because we're basically creating that momentum, right? So it comes in with no momentum in the in the Z direction, and it leaves with negative Z momentum. However, there is a reason why I would have to pull up, and that is to support the weight of the water and the elbow. And you'll notice right here, the water and the elbow have the opposite sign, or at least they have the opposite sign if they were all on the same side of the equation as the momentum flux. Okay, so it depends on how much the water and the elbow weigh. Okay, so F anchor comma Z minus the weight of the water, which is the volume of the water. So this is going to be 0.03 cubic meters. The volume of the water times the specific weight of the water, 9810 newtons per meter cubed. Okay, minus the weight of the elbow given, right? Remember, I just made that number up. So if you work this problem in the book, you're not going to get that same number, right? I could make this number so big that it dwarfs everything else. Okay, the row of the water, well, that's 1,000 kilograms per meter cubed. Okay, negative V2. V2 is 29.285 meters per second times the sine of 60 degrees times that Q, which is 0.23 meters cubed per second. Okay, again, I always like to check my units. Meters cubed is going to cancel with meters cubed, and I'm left with kilograms meters per second squared. Okay, so that's a Newton. Everything else, this one's going to work out to be a Newton because that's going to cancel with that. Okay, so F anchor C. Okay, so this is going to be minus. Let's go ahead and I like to do these things one step at a time, so I can kind of start building my intuition about which terms are the biggest. So this is minus 294.3 newtons minus 100 newtons equals, okay, 1,000 times 29.285 times the sine of 60 times 0.23. Okay, so 5.8 to negative 5.833.2 newtons. Okay, so it should be clear right off the bat that in this case, at least, that's the dominant term. Okay, so we're going to end up getting a negative sign for F anchor Z. Okay, so F anchor comma Z equals that number plus 100 plus 294.3 equals, so negative 62. I don't know what I was looking at. 6227, 6227.5 newtons. Okay, so then I guess F anchor Z equals negative 6.23 kilonewtons. Okay, and I don't remember what F anchor X was. We're out of time, so we'll kind of stop it there. But just remember that when you solve this all the way, that based on what we just said, so it is in fact kind of like this and like that. So when you find your angle, remember you would say, well, F equals whatever the magnitude of F anchor Z is and F anchor X. So F at, now remember your angle is going this way. right? So you need to draw your little angle symbol that way. Okay. And that tells you which way you'd have to push on this to keep it from flying away. Okay, so I'm about 3 minutes over, so I apologize for that. Any questions, concerns, whatnot? Okay, well,
for the magnitude, you just do the 10-year inverse of f of y over f of x.
okay, yeah, for the magnitude, you do, what was, okay, I don't know, I'm hearing myself all of a sudden. Yeah. Hold on, I gotta get rid of this. Okay, it doesn't matter. What was F anchor Z X? What was it?
I don't know what it was, but you just make up a number.
200 kilonewtons. Okay, so you would say the magnitude of F is 200 kilonewtons plus 6.23 kilonewtons squared square root.
Oh,
Right? So that would go right here. And then for your angle, you would go tangent of 6.23 over 200, like that. And then that angle would be measured from the line. Okay. Does that make sense, Paul?
yeah.
Well, you always terrify me that you're driving while I'm in my class. That's terrifying.
I just left the door. I'm about to go play some basketball. But I just be getting confused, like, when they say the magnitude and direction. So like I know what it is, but I be confusing sometimes because the magnitude is when like you do the square the square, you square them, you add them up, you square them, find that, and then like the direction, this one you find the tangent, right?
Wait, when you find the tangent?
I mean, like, yeah, when you find the angle.
Oh yeah. Well, let's do this. Come to office hours and we'll get that ironed out. But right now you're driving, and so let's get that.
Police behind me too.
Let's get that ironed out when you're not driving.
All right.
Okay.
All right.
All right. Anybody else any questions? I mean, I hate to discriminate against somebody who's driving, but if I had to watch a student like get into a crash while I'm explaining how to get the magnitude of the resultant, I mean, it really isn't important compared to not crashing. Anyway, Max Anthony, I know it's just Max. Max, Alvaro, Paul, y'all good?
Yep, all good.
Okay, cool. All right. Well, thanks for coming, guys. I'll see you next time.
All right. Thank you.
All right, thanks, guys.